Hello, in this video we review how to find the intercepts of a graph and help to check for symmetry. Let's get started. So recall that to find x and y intercepts for any equation, we begin by letting x equal 0 to find y intercepts and letting y equal 0 to find x intercepts. So that's always the game plan. So let's take a look at an example of an equation that hopefully you would recognize as a line. So we have the equation 2x plus 3y equals 6. Why do I say it's a line? Well, remember we look at the degree. The highest power here is a 1. So x to the 1, y to the 1. This must be linear. So we're talking about a line. The lines are the easiest to graph. In fact, if you can find an x and a y intercept and connect them, you have your line because 2 points are all you need for a line. So let's see if we can find the x and the y intercept carefully and correctly. We begin to find the x-intercept by letting our y value equal 0. So if you were to let the y value equal 0, this would become 2x plus 3 copies of 0 equaling 6. Well, what does that mean for us? Well, that just means that 2x equals 6. So x must equal, that's it, 3. So whenever y is 0, the only time y is 0 is when x is 3. So if you were thinking of this on a graph, the only time that y is 0 is when x is 3. So when x is 3, that's when y is 0. So that would be that location. That is our x-intercept. Now you could just say 3 and call it a day. Or you could write it as a point. The point would be 3, 0. Either way, we know what you mean. Okay, so we could say the x-intercept is 3 or it is found at the location of 3, 0. What about the y-intercept? Well, for the y-intercept, we would begin by letting x equal 0 in our equation. So if you let x equal 0 instead, you'd have 2 times 0 plus 3 copies of y equaling 6. Well, that would just mean that 3y equals 6. That's right. So dividing both sides by 3, y must be 2. So what does this mean? Well, the y-intercept is said to be 2, or it occurs at the location of 0, 2, because when x is 0, y is 2 at that location. So graphically, that would mean that when x is 0, y is 2, and we would have our y-intercept. Because this is a line, as we mentioned earlier, because its degree is 1, its highest power is 1, we know it's a linear equation. And because it's a linear equation, once you have 2 points, you can connect them and you have a sketch of the line. So I'm going to do that now. Now notice here, we can graph the whole line that way, going through our y-intercept at 2, our x-intercept at 3, and continuing along at the same rate of change. That's the beauty of lines. They continue at the same rate of change. It's constant slope, if you will. Notice that it's also a line that's decreasing from left to right, meaning a negative slope. Now you might think, where did the negative slope come from? But notice that if you had solved for y in this equation, you would have had that 3y equals negative 2x plus 6 by moving 2x to the other side. And then you would have had to divide both sides by whatever's touching y. So dividing all the terms by 3, you would have had your equation in what we call slope-intercept form. I wanted to go through this real quick so you could review with yourself why the slope here is negative. So look at what happens. We'd end up with a negative 2/3 x. So a negative 2/3 is my coefficient of x. And then 6 over 3 is really 2. What is that saying in slope-intercept form? A little review here of lines. Well, that would be that y equals mx plus b, where m was my slope and b was my y-intercept, because whenever x is 0, we get that number, don't we? So our y-intercept should be 2, which we already knew to be the case. And then if we use our slope of negative 2/3, we would go down 2. So our rise would have been negative 2, and we could have gone over 3. Our run would have been positive 3. And we get to the same points on the line. We could have also gone up 2 and left 3, because that's another way of interpreting a negative fraction. But I just wanted to show you that's where the negative slope is coming from. If you actually solved for y there, you'd get a negative m, wouldn't you? Okay, so intercept method, that's what we call this. The intercept method, just getting these 2 points and connecting the dots, is the easiest way to sketch a line if it's in this form. We call the general form here, where we have ax plus by equals some constant. Very nice way to get a graph of a line. So let's have you practice finding intercepts on the next slide. It says find all intercepts and then sketch the line. So again, I recommend strongly that you pause the video, try it yourself, and then see how you did. Here we're told that we have 3x minus 4y is equal to 12. And we want to find our intercepts and graph. Well, to find the x-intercepts, what did we do? We set y equal to 0. So if you set y equal to 0, that would mean that you just have 3x minus 4 copies of 0. You don't have to write that each time. I'm just trying not to lose anybody. Equals 12. 4 times 0 is gone because it's 0. So we just have that 3x equals 12. And we solve for x by dividing by 3. So x must be, that's it, 4. So our x-intercept is 4. Or we could interpret it as the point, x is 4 when y is 0. So on our graph, this would mean we'd go 4 units to the right, wouldn't we, from the origin? And that would be our x-intercept. What about for our y-intercept? What did we do? Yeah, we let x equal 0. So if we let x equal 0, we'd have 3 copies of 0. 3 times 0 is 0, it's gone. Minus 4y equals 12. Just watch your signs here. You really just have negative 4y equaling 12, so that y is just equal to what? Watch your signs. 12 divided by negative 4, it's a negative 3, isn't it? Sign errors are pretty common here, so watch yourself. So we get a negative 3, or the location would be x is 0 when y is negative 3. So 0, negative 3 would be our point. So from the origin, we're just going 3 units down, 1, 2, 3, and connecting our dots, we would have our linear equation graphed. So in this case, that color will not show. Why did I pick that? Sorry. Here we go. 1, 2, 3. There's our y-intercept. Connecting those dots, we'll have our line here. Let's do purple. Now notice that this line would have a negative slope or a positive slope. What do you see there? That's right, a positive slope. In fact, could you tell me the slope if you're really paying attention? It's the rise over the run. So to get from this point, this brown point, which was 0, negative 3, to this red point, which was 4, 0, how much did you rise? Yeah, you rose 3 units. So you went up 3 units. Rise was 3. And how much did you run? That's right, you ran 4 units. And they both went positive directions, right? So positive 3 over 4 would be your slope. In fact, I encourage you by yourself, could you rewrite it in slope-intercept form? And be able to tell that, yes, in fact, the slope is 3/4 positive? Check that yourself and see how you do. Okay, well, at this point, we're going to introduce another discussion of this video topic, which is symmetry. Do we have symmetry? And if we do, what kind? So let's take a look at the definitions. So we begin by noticing that there are 3 types of symmetry that a graph could potentially have. Now, most of the time, graphs don't have any symmetry, but when they do, these are the types that we'll be expecting to see. The first case is kind of boring because it's called x-axis symmetry, and what that means is that if you were to fold the graph over the x-axis, you would be the same units away from the x-axis in both directions. In other words, it's a mirror image or a reflection over the x-axis. So take a look at the picture that we've showed you here. If you were to look at this location for x, at that location for x, it has a positive y value and a negative y value, which are the same number with opposite signs. So maybe it's at y equals 2 and y equals negative 2, right? So at the same x value, the y values are identical except for the opposite signs. So how do you check whether or not a function, an equation, has x-axis symmetry? Actually, it's not a function, I should be careful, an equation. And again, it's not a function because this would fail the vertical line test. The way you can tell that an equation has x-axis symmetry is that if you were to replace every y value with its opposite, so instead of like 2, you replace it with a negative 2, notice that you get the same x value. The graph is unchanged for x, so x stays the same. So when you change the sign of the y value, but you get the same x value for every situation, that must be talking about x-axis symmetry. Notice, though, that x-axis symmetry, those are not functions because they fail the vertical line test. So it's interesting to notice when they happen, but also to mention those are not functions. Now, there are 2 types of symmetry which do happen for functions. So these 2 here, these are functions. And so what kinds of symmetry do functions potentially have? Well, they can have y-axis symmetry, meaning you fold over the y-axis and get a mirror image. And that happens whenever you replace every x value with a negative x value. And notice that the y's stay the same. So at the same y location, you have two different x values that look identical except for opposite signs. So you can find that by replacing every x with negative x, but getting the same y value. Y stays the same. On the other hand, what do we mean by origin symmetry? That was y-axis. What do we mean by origin? With origin symmetry, which we're going to see a lot when we get into trigonometry and other types of graphs, origin symmetry tends to happen when you change the signs of your x values. So notice this x value becomes a negative x, so those changed. But look at your y values. They also changed. Positive y becomes negative y. So this is found for your function when you change the signs of your x values. So both times you're changing the signs of your x values. But this time, y gives you the opposite. Okay? So when you change the signs of your x values and y gives you the opposite, you have origin symmetry. When you change the signs of the x values, but y is the same as you started with, that gives you y-axis symmetry. And again, notice that those two are functions because they pass the vertical line test. Okay, so that's something I would recommend writing down, make flashcards, make note cards, practice memorizing the difference, and also checking with examples so that you can see when it's happening. Okay, so let's take a look at practicing recognizing symmetry. So we have two pictures here in example 2, and we're asked to determine any symmetry that is shown in the graphs below. In A, we see what almost looks like a nice bell, almost like a bell curve. If you studied statistics, you know what I'm talking about. But it's actually part of what we call a sine or a cosine wave in trigonometry, just part of it. So what do we have here? Do you notice any x-axis symmetry, a mirror image over the x-axis? Do you notice any y-axis symmetry, mirror image over the y-axis? Or do you notice any origin symmetry, reflections from quadrant 1 into quadrant 3 or quadrant 2 into quadrant 4? Well, that's right. I notice y-axis symmetry. How do you guarantee or explain that to someone besides the visual? Well, if you were to change the signs of the x values, so for example here, x was 3, and here x was negative. Actually, it looks like you're using smaller units than I was. Let's see, so if this location is 2, then this must be 1. So they're by halves. Each unit is by half. Okay, that's negative 1. So let's take a look. When x is 1, we have this y value of, it looks like half because they're going by halves each time. But when x is negative 1, we have this y value, which is also the same, right? When we're at this location for x, that negative version of that is at the same y value. And we're at this location for x, the y value is also the same. So since we change the sign of x, change the x, we got the same y. When you change the sign of x to its opposite and get the same y, we say that is y-axis symmetry. And when it comes to functions later on, we'll write f of negative x, so I change the signs of my x, gives me the original y value, f of x. So this is how we'll be describing it with function notation later on. But for now, you can just keep in mind, you can see the mirror image over the y-axis, and you notice that when the x values have opposite signs, the y values were unchanged. You got the same y value. Now notice in part B here, on the other hand, with part B here, do we have y-axis symmetry? No, not quite. How about x-axis symmetry? Am I folding over the x-axis? No. But what am I folding over? That's right, I'm folding over the origin. So it looks like here we have origin symmetry. And again, how can I describe that to a reader? Well, notice here when I have a positive, this looks like 1. When I have a positive 1 for x, my y value is at positive 1. But when I have a negative x value of negative 1, my y value is now at the opposite. So when I changed my x, I got the opposite y. Change the sign of my x, I got the opposite y values. In other words, the way that we'll be describing this in function notation soon will be f of negative x. When you change the sign of your x, you actually get the opposite, so a negative f of x, the opposite y value. So that will be how we'll be describing it in function notation. These are our two function types of symmetry, y-axis and origin. Notice if this had been x-axis symmetry, instead of changing the signs of x, we would be changing the signs of y. Okay, so that will definitely take some practice, I promise. Let's take a look at another example. Here they ask us to complete the graph by using the symmetry that they've told us we have. Here they say we have x-axis symmetry. So what does that mean? It's a mirror image over the x-axis. So what does that mean? When I change y values, what should happen? My x values should be the same. What does that mean? Well, you can't really change a y value of 0. That's still 0. But here the y value was 2. Can we change that to a -2? Where would that be? -1, -2. And we keep our x value the same. Okay? What about for the y value of, it looks like 3 at x equals 5? Keeping x at 5, now our y value should be at -3, so down here. And we could continue doing that to get our picture. Let me grab another color here for you to see. So what does this graph end up looking like since it's supposed to have x-axis symmetry? Almost like a parabola on its side. If you remember parabolas, we'll be studying them some more as the semester progresses. But this would be our picture, right? A parabola on its side, basically, because of the information they gave us about having x-axis symmetry. Now, if they had given us a different type of symmetry, this would be a very different graph. But notice that wouldn't have happened because it extends beyond the origin here. If it had gone until the origin, you could have shown maybe y-axis symmetry, or if they had asked for origin symmetry, you could have gone down here and shown some type of, almost like a snake in that case. Okay, so getting used to the types of symmetry will take practice. And again, I highly, highly recommend you using note cards in order to feel better about that. Let's do one more example and see how all of this is coming together for you. To your current page and go. Example 4 tells us, could we find all intercepts, so let's practice our first skills from earlier, and then discuss potential symmetry for the equation x squared minus y minus 4 equaling 0. So to begin, we could notice that this is not a line. How do I know that? It's not linear. That's right, because my degree is what here? The highest power that you see is 2. In fact, we're going to remember that as we go through higher and higher degrees, they tell us something about the shape of the graph. Degree 1, it's a line. Degree 2, it's a parabola. Degree 3, it'll be a snake. We'll be learning more about that as we get into other videos coming soon. But for now, I know it's definitely not a line. What else can I do? Well, I can find the x-intercepts. So let's take a look at how we did that. To find our x-intercepts, remember, that's where we let y equals 0. So this would become x squared minus 0 minus 4 equals 0. What does that mean? Well, that would mean that x squared minus 4 equals 0. Now, there's a couple of ways to solve this degree 2 equation, quadratic equation, that we've reviewed in our previous videos. Feel free to go back to them if you need to. One way is you could always try to factor, and this one does factor into a difference of 2 squares. So if you factored it, that's one way, x plus 2 and x minus 2, and set it equal to 0. Then we have the zero product rule. Since something times something equals 0, we know that one of those factors, or both of them, has to equal 0 at some location for x. So it would turn out that x would equal either -2 or +2. So plus or minus 2. Those would be my 2x intercepts. Or I could have used the square root method and got an x squared by itself by adding 4 to both sides and eventually taking the plus or minus square root. Now watch out there. A lot of students forget the plus or minus sign and they'll only get +2 instead of positive and -2. So be very careful there. So what are the locations of your x-intercepts? Well, you could just say plus or minus 2. That's what they are. But their locations would be at positive or -2, comma, 0. +2, 0, and -2, 0. So as far as the graph is concerned, if I was doing a little sketch here, we have x-intercepts at -2, 0, and at +2, 0. So those are my two x-intercepts. Let's talk y-intercepts. How did we find y-intercepts? By letting x equal 0. So if x was 0 instead, you'd get 0 squared minus y minus 4 equaling 0. What does that mean? Well, we have a linear equation. So we would have -y, or if you like, you could just move y to the other side right now, make it positive. That's what I would choose. So now it's +y when you add it to the other side equals a -4. Otherwise, you'd have negative y equals positive 4 and then have to divide by negative 1. Eventually, either way, you should be getting that y is negative 4. So the y-intercept is only one of them, and that makes sense because this is a function. Can't have more than one y-intercept for functions. The location would be when x is 0, y must be negative 4. So 0, negative 4. So what does that look like on our graph? Just go down 4 units from the origin. So that would be the location of our y-intercept. So if we have 2 x-intercepts and 1 y-intercept, and it's a degree 2, which will tell us, hopefully as we get more into this, that'll tell us this is a parabola. We could then connect our dots and form a parabola opening up, and we'll study more about why it's opening up as we get into future videos together, future chapters. So this is a situation where we have a parabola opening up, and that turns out to have something to do with a positive leading coefficient of 1. It means it's going up instead of down. If it was negative, it would go down. And now the final question is, can we describe symmetry? Well, by looking at the graph, you can kind of answer the question, right? This is a mirror image about the y-axis. So yeah, it does appear to have y-axis symmetry. But you don't want to just declare that unless you absolutely know for sure that that is correct. So how do you check for symmetry? Well, to check for symmetry, what I recommend you do, especially if you think you have a certain type of symmetry, is to replace every x with a negative x. So in this case, change x's and see what happens. If you change your x values, what would that mean here? Well, in the original, you had x squared, but now you would have negative x getting squared, minus y minus 4 equaling 0. So we've changed the sign of our x value. So let's see what happened. A negative times a negative is a positive. So this is the same as just x squared, minus y minus 4 equaling 0. Looking at the equation now, what you want to ask yourself is, do I have exactly the same thing I started with? Do I have exactly the opposite that I started with? Or do I have a mixture? Notice that x squared looks exactly the way it started. Negative y, exactly the same sign as it started with. Negative 4, exactly the same as it started with. So this is the same as the original, which means the y values are staying the same. Overall, the function has not changed. So when you have the opposite x values, you end up with the same y values. And that's what happened here. When we had opposite x values in our graph here, negative 2, positive 2, when we had opposite x values, they stayed at the same y level. This is telling us that we do in fact have y-axis symmetry. If, on the other hand, you got the opposite y value when you changed x, that would mean you'd have origin symmetry. And if you had changed the signs of the y values instead, but the x values stayed the same, that would mean you'd have x-axis symmetry. But once you found the one, you can probably be safe to stop unless you have a circle which has multiple types. So those are the only ones that are a little funkier. Okay, so we've done a lot in this video. We reviewed how to find x and y intercepts, and then we described what symmetry looks like. Again, I highly recommend you make note cards, you practice the different types, you write out the reasons why you're saying what you're saying each time until you really fully understand symmetry. It'll be really important, not only in this class, but in your future math classes. So that's it for this video. I hope you practice and you let me know if you have any questions. Remember, math is not a spectator sport. I'll see you next time.